Hi, everyone. My name is Sophie Tian, and I am an applied ML intern at the Vector Institute. Today, I'll be presenting a demo on differential privacy with TensorFlow Privacy Library, or TFP. The differential privacy is a field that tries to ensure statistical analysis does not compromise privacy. It measures the privacy leakage of a randomized algorithm and provides formal privacy budgeting on the analysis we want to do. And perfect privacy is achieved when a machine learning model makes the same predictions on any pair of data sets that only differ by one data point. The intuition is that if a particular data point does not affect the outcome of learning, then this person's information cannot be memorized and their privacy is respected. So in deep learning, we achieve differential privacy with the differentially private stochastic gradient descent, or DPSGD. The main idea is to add noise to the gradients used in SGD so that each data entry has plausible deniability. And specifically, there are two modifications made to the vanilla SGD algorithm. The first is that the sensitivity of each gradient needs to be bounded using gradient clipping. And the second is that we will sample some noise and add it to the clipped gradients. And this is to make the algorithm's behavior more random. Now that we know about these basic concepts, let's see how it's applied on a real-world dataset. For today, I'll be using the heart disease prediction dataset, which is a small-scale binary classification dataset hosted on Kaggle. Our goal here is to predict whether the patient has heart disease or not. For the sake of time, I've omitted some of the exploratory analysis and pre-processing tasks required, such as checking that we don't need to worry about imbalanced classification or imputing any of the missing data, performing the one-hot encoding and to convert categorical features, performing normalization of the input values to help the model convergence, as well as performing the train test split. So having done all of these steps, let's see how we can implement a differentially private Keras model using TFP. Basically, the biggest implementation change is to change the vanilla optimizer into its differentially private counterpart. And all other aspects of training, such as the model architecture or the training loop, will remain the same. For today, we'll be using DPSGD optimizer, but TFP library also provides other implementations such as DP-ADAM, DP-ADAGRAD, etc. So for a vanilla SGD model, we're using the standard SGD optimizer in the Keras library. And for our task, since we're doing binary classification, here the loss function is a binary cross entropy loss. To turn this into the differentially private counterpart, we will use the DPSGD model from the TFP library. And here we see that this DP Keras SGD optimizer requires 4 hyperparameters. The first one is O2 norm clip, which is to specify how much we will clip the gradient to limit the amount of contribution from individual data points. And the second is the noise multiplier, which is used to specify how much random noise to add to the clipped gradients. We also have the number of microbatches, which is used to split up each batch of data, as well as the learning rate, which is a very standard hyperparameter. So the 4 of these hyperparameters together will affect the amount of privacy guarantees provided. And as for the loss function, we're using the same function as before, but here we're specifying that we want a vector of per example losses rather than its mean over a mini batch. So to understand the DP guarantees provided in an ML algorithm, 2 metrics are used. The first one is delta, which is the probability of the privacy guarantee not holding or the probability of an information leak. Typically, we set delta to be a very small value depending on the size of the data set. The second metric is epsilon, which stands for the strength of the privacy guarantee. Epsilon measures the amount of privacy loss when we change a single data point in the database, and the smaller value of epsilon corresponds to a better privacy guarantee. So after training a differentially private ML model, we need to understand how much privacy is provided by the model, which is the value of epsilon. So this will depend on the hyperparameter values we use for the DP optimizer, as well as the size of the data set, which will influence our selection of the value of delta. The actual calculations for the privacy guarantees is a functionality provided by the TFP library, and we can simply call the functions with the following required inputs: the number of epochs, size of training data, batch size, and a noise multiplier. So now I've provided all of the basics you need to know about DP and implementing a DPSGD model. So let's get into model training and see how a vanilla SGD model compares to a DPSGD model. First, let's select some hyperparameter values that both as the vanilla SGD and the DP-SGD models will use. For time's sake, I'm just going to go for like a larger learning rate value and select a smaller number of epochs. So here I have 80. And for DP-SGD, there are some additional hyperparameters that we need to select. And here I have the L2 norm clip and the noise multiplier as an example. So suppose we first select a small value for the L2 norm clip, which means that each training data point can only contribute to the model by a small amount. And let's choose a very large noise multiplier, which means that we will add a lot of noise to the clip's gradients. And let's run the models and see how this works, or how this performs. So when we limit the contribution from individual data points, as well as adding a lot of noise, we would expect that the DP-SGD will not perform very well because so much noise has been added, but it will be very private. So as we can see here, the DP-SGD model does not perform as well as the vanilla SGD model in terms of the test accuracy, but we have a pretty decent epsilon value here, which is 4.1995. So an epsilon of any epsilon value below 10 is typically desirable. So now this is a pretty good epsilon. And now let's see what happens if we allow each data point to contribute a little more to the model. So that means we're sending a higher L2 norm clip. And let's reduce the noise that we add to the clipped gradients by a little bit and see how this model performs now. So hopefully we would see that the model performs a little better right now. But as we expect, we're adding a lot less noise than before. So the model will be a lot less private, which corresponds to a higher epsilon value. As you can see now, the epsilon value is closer to 47 now, which is nothing near desirable for sure. And the test accuracy is pretty suboptimal. So we're not really there yet. But in some of the runs, I found that I was able to find a good epsilon and a good test accuracy for the DP-SGD model. So to summarize, there is this privacy utility trade-off in differential privacy. When we strive for more privacy, the utility of the model often decreases because we clip the gradients too much, or too much noise has been added to the gradients. So for different applications, we need to think about how sensitive the data is and then go from there. And next, let's look at an adversarial example. In differential privacy, the main focus is whether an adversary can detect a differential change in the dataset. Now we will compare how the vanilla SGD model and the DP-SGD model change when we remove one data point from the dataset. So now let's first create a second adversarial dataset by removing an entry within the training set. So I have a slider of the indices of all of the training data points. So I'm just going to randomly select one. Here I have the data index 90. And let's remove that data point from the model or from the training data set. And for verification, we can see that the shape of the original training set had 193 rows. And now this adversarial data set has 192 rows. And now we want to compare how much the model parameters changed when we use the original training set versus when we use this adversarial training set with one data point removed. So for fairness in the model comparison, I'm resetting the seed before training each individual model. Let me first click the button to start the training. So here we are training two pairs or four models. The first pair is the vanilla SGD model with the original training set and a vanilla SGD model with the adversarial training set. And the second pair of models are the DP-SGD model with the original training set and the DP-SGD model with the adversarial training set. So what we want to know is how much the model parameters changed going from this one to this one. So between the first pair of models and between the second pair of models. So what we would expect is that the first pair of models trained with SGD will be more different than the second pair of models trained with DP-SGD, because DP-SGD is limiting the contribution that each individual data point can make. So now we see the results here. We see that going from between the first pair of models and the second pair of models, the changes in the parameter values are both quite small. But DP-SGD made the adversarial example less detectable by a magnitude of 5. So to recap, DP-SGD reduces the influence of each individual data point. So when we train a model without a particular data point, DP-SGD makes the model parameters change less than vanilla SGD. As a result, the adversary has a harder time determining whether this person is in the database, and as a result, their privacy would be better protected. In summary, in this demo, I have introduced you to differential privacy and shown an implementation of DP using the TensorFlow Privacy library on the heart disease prediction dataset. The changes required to make a model differentially private include first, replacing a regular optimizer with its differentially private counterpart, and second, calculating the privacy guarantees provided or the epsilon value using the functions provided by the TFP library. And to recap, DP in deep learning is achieved by gradient clipping and adding noise to the clipped gradients. Also note that there is a privacy utility trade-off, and we need to determine an acceptable amount of utility and a minimum amount of privacy requirement before training our machine learning models. And finally, I've shown you a comparison between the vanilla SGD model and DP SGD model on the adversarial example, and demonstrated that DP SGD made the differential changing dataset less detectable by several magnitudes. And thank you, everyone. That's it for my presentation.